Okay. So the scope of 3D metals in transfer hydrogenation has been totally unexplored, and it started maybe 2 years ago or so, 3, where a good few catalysts have been discovered. There's 2 issues with with first-row transition metals. Their catalytic application has been underdeveloped because it's hard to predefine their coordinative environment. So many people have struggled to make proper compounds, properly defined compounds. Some of them are dynamic, some of them are very sensitive to all types of additives. So like some bases have been for a long time totally killing for the activity. And the other thing that played quite a role is that many of these first-row transition metals are hard. So their affinity for hydrides is relatively low, and that precluded some of the activity. Now this changed. So we know from cobalt catalysts that are very nice hydrogenation catalysts. We know from iron catalysts that do this. Maybe I shouldn't tell you, but we started looking into manganese as well, and others have done this too. So there's a wave of using manganese for both hydrogenation and transfer hydrogenation. And this has been used for formic acid as well by some groups in Austria, in Italy. In Germany, Beller Group has looked at manganese for hydrogenation, transfer hydrogenation. So this, I'd say, we'd see in the next 3-4 years, we see a massive explosion of that area. And people understand more and more how to, so I think the last 3-4 years, it has become a very, very trendy to use iron, manganese, nickel, so the cheap metals for catalysis. People have for a long time thought, oh, this is, take the Caribbean area that hasn't migrated much in this field, because you often work with paramagnetic systems. So your structural data are not that compelling. So people took much more pleasure to work with iridium, with ruthenium, because everything is diamagnetic. You have absolute control what you're having. I think the more we know about those metals, the more we can extrapolate to those paramagnetic systems, and the more we can work with it. And there have been a huge wave the last 5 years in using those earth-abundant metals. And as a consequence, now we can use them for catalysis. So I think in the next 5 years we see a huge boost of these systems exactly for this type of reactions that we always thought, well, low hydride character, very base unstable, so it won't work. Actually it does. Very nice. Very good results. And there's, with some fantasy, with some imagination, you get stellar papers out. Now I have to add, there's a bit of a flaw and a bit of a hype with it. Everybody talks about, how cheap iron is, how cheap manganese is. One half forgets that their ligands cost by now about 10 times as much as the metal. But already here, with many of those systems, the assembly of the ligand, the efforts you need to prepare the ligand and to install it, is maybe 3 times the cost of the metal, even if you use precious metals. All these chiral asymmetric systems, the making of the chiral phosphine or the chiral amine, that's the cost for the ligand, that's the cost for the metal. So why do you focus on, oh, but it's a precious metal? No, for God's sake, it's a precious ligand. You have to make that ligand cheaper. So that's one half. The other half is that if iridium reaches 50,000 turnovers and iron reaches 100 turnovers, that's respectable, 100 turnovers with iron. But if you need shovels of iron to get something, you produce tons of waste. Iridium we can recycle. Iron recycling? No, you're kidding. Costs too much energy. So the sustainability has their 2 sides. At the moment, it's all a hype of, use rusty metals, use those first-row transition metals, they're cheap and they're abundant. But we forget that all the iridium, all the palladium, all the ruthenium, all the rhodium, we totally recover. We don't waste it. We reuse it. It's not gone. But all the iron, all the manganese, all the nickel, So what else can we do with dehydrogenation or with this transfer hydrogenation? We can do very elegant functional group transformation. And I'd say one of the hallmarks is the transformation of alcohols and amines to peptidic bonds, which has of course a huge biological relevance. If you do a retrosynthesis of peptide bonds, you come up with amino acids with amines, but then you have to manipulate them. You have to activate your acid into an activated ester. You need coupling agents like DCC or HATU or whatever you're using. You generate a big lump of waste. B, you have to manipulate your reagents. Now this is a very easy precursor, and you don't have to manipulate anything. And with such type of ruthenium precursors, you dehydrogenate the alcohol, you dehydrogenate the imine, and you form this compound. You form the hemiacetal, hemiaminal, and this hemiaminal can then be dehydrogenated further. Now, there's some subtleties in this reaction, and I hope, yes, I do have the mechanism for this reaction. There's some subtleties. First, this ligand here is a peculiar ligand, because if you pay careful attention, you see that this is not a pyridine, but this is a dearomatized pyridine. This pyridine here has acidic benzylic groups, and in one of the forms, this benzylic group has been deprotonated, and you have an exocyclic double bond. As a consequence, this is not an imine, the nitrogen here, but it's amide formally. So it's an anionic ligand, an anionic hydride, so this is ruthenium 2. But you'd see already how this system can reversibly flip that double bond back into the ring. You gain aromatization, and you hydrogenate this position here. So this is a proton acceptor, this is a hydride acceptor. This is the compound we started with. If this reacts with an alcohol, which has a proton and a hydridic group here, we see that the compound is rearomatized. We form this alkoxide, and the proton ends up at this phosphenic position here. So basically this double bond flips to grab the proton, the lone pair on nitrogen flips over to rearomatize. So we have an imine and two anionic ligands on the ruthenium, the oxide and the hydride. And then this undergoes a beta hydrogen elimination. One arm of this pincer ligand flips open, and we have two hydrides and the ketone group. And now it depends really on what's the donor strength of this L group here. If it is a strong donor, like a phosphine, you have a very rapid recoordination. Then this alkoxide here, this ketone here is displaced. The nitrogen, the phosphine binds back, and we get back this type of formula, but now a hydride here instead of the alkoxide. So we release the aldehyde. This aldehyde reacts with the amine in solution in a Schiff base reaction, and we form the imine. So that's one course of reaction. And then you'd see this can then undergo, so here is the phosphine pincer, and this can then undergo a dehydrogenation. We lose that proton here, that hydride, and we're back in this system here. If this is a loosely bound ligand that has a weak affinity, like an amine, which is sterically protected, cannot bind very strongly, and the nitrogen is a relatively hard ligand, so the ketone is in competition, not like with the phosphine, where the phosphine wins always. Here the ketone wins. So it stays coordinated, and the amine doesn't attack the free aldehyde, but it attacks this metal-bound aldehyde. As a consequence, the hemiaminal that is formed here in the Schiff-base reaction, the hemiaminal is formed. If this is just a loose reaction, this dehydrates and you form the imine. That's the classic Schiff-base reactivity. If this stays in the metal coordination sphere, the dehydration doesn't occur because you have the ruthenium bound to the oxygen. Instead, we get a dehydrogenation. So this proton here is removed and we form the amide. So the key here is the donor strength of your ligand L here. If it's a strongly donating ligand, if it's a very good match with the ruthenium, we form imines. If it's a poor match, the hemiaminal stays in the coordination sphere of the metal, and we get, instead of imine formation, we keep the hemiaminal in the coordination sphere and we get the peptide. This is industrially very relevant because if you think of many polypeptides are used for all types of electronic materials. Polylysine is used for medical applications because it's very biocompatible. So you have huge advantages of having very cheap starting materials and alcohol and an amine to form amino acids. You can also think of all the nylon industry. You know, to fabricate nylon, you typically use the anhydride or the dicarboxylic acid chloride, and you synthesize, you react it with a diamine. Now here you don't have to prepare this high reactive anhydrides or acid chlorides. You can simply use a diol, a diamine, you mix them together, you polymerize it up. So you have a very nice process to make nylon in all types of flavors. You can also think of an amino alcohol, where either you form cyclic or polymeric product. So huge application potential, and that's as well why this has generated quite some huff. And depending on the ligand and its structure, and that's especially work from David Milstein in Israel, you can use slight modifications. So with the donor strengths of the pincer arms, like here the phosphine versus the amine, with the steric constraints and the bite angle. So this anthracene-derived scaffold has different bite angles, different stabilities. You get different reactions. So with this one here, for example, you can make, out of two alcohols, you can make the acetyl. If you use the same alcohols with this catalyst, you form esters. And of course, you can drive the reaction one way or the other. So they have used this catalyst also to hydrogenate esters very easily. Very nice. And then maybe really as an end flavor, and I don't want to go too much in detail, the same transfer hydrogenation nature of course uses for building up energy. So it would be nice if we can use the same. So nature uses solar to power their system, but they do huge transfer hydrogenations, for example in photosynthesis, where protons are removed from water, added to carbon dioxide and stored as bonds, as chemical bonds in carbohydrates. So this is a very efficient method, and you have basically a transfer of hydrogen from oxygen to carbon, and that brings us then to carbohydrates. And we have to think of three different processes of this transfer, and we've seen two of those processes already in transfer hydrogenation. So we can have either proton transfer, that's acid-base reactions. We can have hydrogen transfer, so hydrogen atom transfer. That's when we simultaneously transfer a proton and an electron. Or we can have hydride transfer. And nature, of course, has hydride transfers, but they're never actually hydrides. Nature, apart from hydrogenases, like iron-iron, the iron-nickel hydrogenases, nature doesn't transfer hydrides. Nature does rarely generate hydrides. So in most of the cases, the hydride is actually not a hydride that is transferred, but it's a proton and two electrons, which is then the equivalent of a hydride. So these systems, and that's what we do here. So we do a redox reaction and hydrogen transfers. So in order to have the proton and the electron transferred, we have not only to understand the proton, how the proton is moved, but as well how the electron is moved. So I've compiled you here just very briefly the a recapitulation of electron transfer processes. I'm sure you've heard this during your undergraduate work already, but we can define 3 different transfers which have different rates and different prospects. So one is the outer sphere electron transfer, where the electron is transferred through an outer sphere process without changing the inner sphere of the metal coordination, which is shown here. So where basically the oxidant and the reductant meet each other in an encounter complex, and as the complex as they come close, the electron hops from iron to iridium. The iridium is reduced, the iron is oxidized, and we get an electron transfer. These outer sphere processes are extremely fast, diffusion controlled essentially. Because it's really just a check of how do they diffuse together. A bit slower are the inner sphere electron transfer processes, where not only where the coordination sphere of the metal center is actually changed. Exemplified here with a cobalt-chromium system, where the chloride bound to cobalt is ending up in the after the redox reaction at chromium. So here the inner coordination sphere changes. This, I changed the ligands here as well, so that if you do this in an aqueous ammonia reaction, you'd see that there's always a bit of ammonia, a bit of water that can come up for the outer sphere, for the other ligands. But the transition state here is a bridged chloro compound, where the mu chloride is bridging the cobalt and the chromium, and as the chloride is migrating from one atom of metal to the other one, the electrons are moving as well. So this transition state here requires bond making and bond breaking, so it's a bit slower than the outer sphere processes, but still relatively fast. You'd see very fast rates. Then we have a third process which is typically very slow, and that's a process where we have multi-electron transfers, which are often multi-step processes. So here we have a transfer where one ion undergoes one electron transfer process, whereas the other one undergoes a 2 electron transfer process. So we have different steps involved. So we cannot have such a process easily, and we cannot have such a process because there have to be 3 parties to come together. So this is very slow typically, because if we transfer 1 electron from iron to thallium here, we generate a thallium compound that is very unstable. Thallium-2 has a very negative potential, so there's a huge penalty in generating that intermediate. And that's typically the case for all multi-step processes. The formation of an intermediate is disfavored, it's very unstable, it's very hard to reach. So that's why multi-electron transfer processes are typically slow. But that's the problem with oxidizing water. You have a multi-step process, you generate 4 protons, 4 electrons, you don't have that easily a acceptor that accepts at the same time 4 electrons. So here's our problem with water oxidation, and you recall water oxidation is required here. We formally make out of water dioxygen, we release the protons to reduce the carbon dioxide. So that's the hard bit in all the photosynthesis that is natural and artificial. We have here a huge penalty in transferring these 4 electrons. And that's as well, in addition to this, we have the high redox potential for water oxidation that we somehow have to overcome. We get a penalty if we transfer only the electron, we reach a high energy transition state. Generally, if we can do a coupled transfer of proton and an electron simultaneously, we gain a lot. So that's basically what we do in transfer hydrogenation. The metal absorbs the proton and the electron at the same time. So that's a bonus. I'm nearly done. I didn't got that.
Analyzing this coupled transfer, that is what is done in a photoelectrochemical cell. In one compartment, one reaction is done, in the other compartment.
Yes. So electron transfers can be spatially separated. Yes. And so you transfer in one compartment the electron, but that's cycled. Yeah. So I'll just show you 2 examples to exemplify that case of protons and electrons need to travel together. how much this facilitates reactions. And then we stop. I hope. We do this in the afternoon. Yes, we make a break, I come back to the proton-coupled electron transfers. Enjoy your lunch break. 2, we meet here again. Now this is recorded, I can have that course every year here at IIT, and I just put it on the screen, and you, you guys Skype me when you have a question. No, it's much easier if we can talk. So we'll make it a bit lighter this afternoon. So I dwell a bit more on the proton-coupled electron transfer process. Maybe we do 2-3 exercises, and we see how this goes. Yeah. So I started telling you a bit about the problem of these type of processes, that they require not only protons to transfer, but also electrons to transfer. At the same time, this is a super important reaction because it is related to how we can capture energy and store it. So this is important because it's photosynthesis, so it basically captures solar energy, which is the most abundant energy we're having on the planet. And it's renewable, and it's very practical. If you're in India at such a day like today, you have plenty of this energy. The problem is, most of this energy we're happy to somehow protect ourselves, but in fact it would be nice if we can store it and use it when we need it. So storage is an important aspect. Harvesting, storage, utilization. That are the 3 key points that we need to address when we look at sustainable energy production. But it would be much nicer to use this energy than to dig for oil and other fossil fuels that we just know that even with cracking and fracking and whatever is out there, we will deplete this energy. We consume it so much faster than it's used, this won't last forever. And with growing populations globally, there's no point, to say, look, we all have to cap our CO2 emission, because we cannot stop developing countries from developing, and that's all countries in the globe. You cannot say in African country, oh, you can't industrialize because we have to stop the CO2 production. That doesn't work. So we need a much more sustainable solution to this. There's different energy sources that are totally sustainable. One would be wave energy from oceans. Another one would be wind energy. And the third one is solar energy, and by far the most abundant is solar energy. Wave energy is very much in its infancy. We have very little tools to capture wave energy sustainably. Wind energy is, of course, already produced and utilized. And there is, of course, the fourth one is geothermal, which is unfortunately very specific. So New Zealand has quite a bit of of geothermal reservoirs. There's some places in the US where you have lots of geothermal reservoirs. Iceland is a fantastic country on this aspect because they can really power their whole economy with geothermal energy. So, Iceland is far up north, very close to Greenland and to the North Pole. It's shivering cold. Now it's maybe 4 degrees during the day, so nothing to write home. But they can grow bananas because they have the geothermal reservoirs, so they can build greenhouses that are just geothermally driven, totally natural resources, no depletion, and they have strawberry and banana fields. Very nice. So they are totally autark. So all the energy they're using, they're taking it from the ground without depleting anything. But that's very specific. That goes only for certain areas where you have volcanic activity, geothermal activity. In most of the places, it doesn't really work. So Probably wind and solar are the most developed, and you know that we can capture solar energy to some extent with photovoltaics. So the transformation of solar to electricity is a thing we already have technologies that work not too badly. Still, it needs lots of development. Efficiency is not great, but it's improved steadily. So I don't know whether you've seen the recent news that we're now at 27% efficiency of transforming solar to photovoltaics with silicium. So with elemental silicon, crystalline silicon. The other thing, of course, is storage. So it would be nice if we can store it in fuel rather than in electricity, because electricity is only counting for maybe 10%, maybe a bit less than 10% of our energy consumption. Much of the energy consumption is actually used to power engines, and there's much more of the engines are powered by oil, gas, diesel. So we need to replace those. And that's where the solar system comes into the game, and the storage of this energy, not in carbohydrates, but in other chemical bonds. So when you can store this in chemical bonds and then cleave those bonds exothermally, we generate that energy to power things. And we have already engines that work very well on hydrogen, so hydrogen would be the ideal fuel. And the ideal storage of hydrogen would be water. Because then you have a very sustainable cycle. You first oxidize water.
That we are improving solar, and we fundamentally need to improve the efficiency of the solar cell.
Yeah.
This 27% has to be improved. So I was wondering that even if it is improved to say 100%, so let's say it is a 4-time improvement, that is the maximum improvement that we can do, the maximum development that we can do in this area.
Yes, I think the maximum is not even that high, because you always have heat and other dissemination. I think the maximum is about 30% you can really achieve.
Yeah, so what I was saying, that even if it reaches 100%,
yeah?
like in US, the present amount of energy that is coming from solar in the whole proportion is 0.04% of the total energy is coming from solar. So even if the efficiency is improved to 100%, like that would be only a 4-fold increase. So will that number be any significantly changing of that proportion of total energy that is coming from solar?
So yes, there's you're addressing there a few important points, but some of them are mixed up a bit. So the efficiency of solar cells is only on photovoltaics. So solar cells only fuel in so we have like two components we have to look. So which type of energy do we use? So I think it's about 8% is electricity. There's much more energy is fuel. That's maybe 80 to 90%. That's actually not true. It's more 60 to 70%, and then heat and buildings and so is taking up another 20%. So if we talk about photovoltaics, we only talk about that bit. So then you address the question, where is the energy coming from that we use? And there you have a different pillar. And you have biomass, fossil, nuclear, how much more? So here's, so that maybe that just gives us the picture, but it's probably useful to have the context. So here you see who uses energy. Who uses the energy, and you see there's there's the OECD countries are playing a big part. That's the US and much of Western Europe. What's it? The OECD. Do I have it somewhere? That's weird, huh? So the OECD are the what's the I forgot the abbreviation. It's a lot of Western Europe. The US is part of it. Canada, and then here is growing Asia, which is growing over the last 20 years. That you see here, it will grow a bit more. Africa will grow a bit. Africa is the blue one, huh? So it's small, but it will grow. But the important piece is that, you know, this is, the growing is because we develop further and further and the population is growing. And more people need more energy, period. So if you want to solve the energy problem sustainably, we'd say we need less people. So that's unethical. Huh? So, but that's the use of energy. Here you see where is it coming from? And you see natural gas plays a big role, other liquids, coal, nuclear plays a small role, 8% still, biofuels a bit, liquid biofuels and biofuels together are up for 9%, so renewables. So we're talking about 9% of the total energy resources are coming from more or less sustainable renewable resources. And all the others, so coal is different, but then petroleum and liquids and natural gas, so that's all the fossil fuels, they make up for 70%. Nuclear goes exclusively to electricity. Do I have the thing? Oh, no, I don't have but so the thing of having a higher efficiency makes photovoltaics more interesting, but it makes only photovoltaics for electricity more interesting. Whether we improve those 10 or 11% is not dependent on the efficiency, but much more dependent on whether we have the infrastructure to do it and whether we make that shift. But so as long as we can't produce hydrogen or electricity sustainably, electrical cars or hydrogen-driven cars are a farce. So these days, like Toyota has a hybrid system that works on hydrogen. So we have the hydrogen cars, which is nice because we know that cars can easily drive on hydrogen. So the technology is there. The disadvantage is that all the hydrogen that we get to drive those cars, you know, they of course, when they burn, they only burn hydrogen, so we get water, very clean car, no CO2 emission. Plenty of CO2 emission. Hydrogen is coming from cracking, from what's it called? Steam reforming. And steam reforming is nothing else than oxidizing hydrocarbons to carbon monoxide and dihydrogen. So, and the carbon monoxide is then oxidized to carbon dioxide. So you form the CO2 not in the car, but you form it when you produce the dihydrogen. But it's exactly the same amount of CO2 essentially. So this only becomes sustainable once we have an efficient process to form dihydrogen. That's for fuels. But the same holds for anything else. So we need to have a technical possibility to generate dihydrogen or electricity, but sustainably. Nuclear, difficult, huh? We've seen in Japan, we know that the waste will be for hundreds of generations after us. They have to cope with that waste. Problematic. So nuclear is CO2 free, but it generates a load of crap. And the dihydrogen, we need to have processes that form dihydrogen sustainably. The steam reforming is not the way to go. Efficiency is important to help the technology to break through. But already now we don't have super efficient, or we can improve of efficiency, but already now buildings work on solar fuel, on photovoltaics, buildings work on solar power. So already now we have the infrastructure there. If we have higher efficiency, cheaper production costs, the better. And the faster this process goes. But the idea is not to improve necessarily the efficiency of these 9% here, but to start making some of those 36 much lower and increase the percentage. So efficiency is one part, and technology, or having the techniques, the scientific processes, is another part. They work hopefully in parallel to help to solve the issue.
As well as
yeah. So that's the context of making this happen. Now the ideal case, I'd say, so there are different options to generate dihydrogen, and I haven't a slide, but really, so people have looked at ammonia borane as the dihydrogen source. So you in the extreme case you form you form much more. So you form then 3 times dihydrogen. This has a super high capacity, hydrogen storage capacity, because the weight of nitrogen borane is very low compared to the dihydrogen that you produce. So it has a very high hydrogen storage capacity. Even a bit lower is methanol. Because here you have carbon and oxygen, which are heavier than boron and nitrogen together. And in the presence of oxygen, you form 2 equivalents of carbon dioxide, 1 equivalent of carbon dioxide and 2 equivalents of dihydrogen. So in order to this, and then the last one, obviously, would be water. And water is ideal because you'd see you have 1 oxygen, so it's not as high a storage capacity as ammonia borane, but it's extremely clean. So in all those cases, the problem is, and this has been explored to almost to death in the US because they banked really on ammonia borane as the hydrogen fuel, and there's no efficient regeneration because you get polymers and you get all types of things. So much of the US has dropped the ammonia borane economy because of difficulties in recycling. This one here is currently still very much followed, and you see there's a stepwise process, and some of you guys are contributing to this. Because you can step it. So you first get formic acid, and then you release a second CO2, and you oxidize it further and you get CO2. And that's at the moment very much in progress because both this you guys know that this is reversible. And there's a second one. With catalysts, we can reverse the formic acid to methanol reversibility. So now we have a fuel cell that works methanol CO2 relatively efficiently. Now, one of the big issues here is that the CO2, unfortunately, is a gas. So this is not easy to handle to hydrogenate CO2 to formic acid. So, and at the same time, it's not easy to stop the oxidation of methanol to formic acid. Typically, this is more reactive than this one here, so you end up in 1G. So well, this one is relatively good. This one is not so. So this is the bottleneck at this reaction. With the water, we have a different scenario. Let me see whether I explained this a bit. I'm hopping a bit, but I hope it's not too messy. So with the water, we have a different scenario because we can use, we can basically separate the two cycles into two half reactions with the water, like nature does basically with the carbon dioxide and the photosynthesis. So we have on one hand side the oxidation of water to dioxygen, and we have, that's the water oxidation cycle, and we have on the other hand side the water reduction cycle where we reduce the protons to dihydrogen. So we have those two half cycles, or those two cycles that we have to manage both. Once we manage this, the regeneration is very easy. Hydrogen burning just gives you back the water, so you don't deplete water, you don't use water, you don't use the water, you just transform it back. So it's not that we use the water, but we just regenerate it. But so, in water oxidation, we basically have the water oxidation cycle and the water reduction cycle. This one, we know water reduction is thermoneutral at 0 volts. We have plenty of catalysts, electrodes, but even iron and nickel catalysts that do this very efficiently, very easily, high turnovers, millions. So we can produce the dihydrogen. Only we use it from protons, so it's not sustainable. We have to use it water. And so for this to become sustainable, we have to manage the more difficult part. That's multi-step, multi-electron process to generate out of O2 minus dioxygen. I'm not following you. So I say the water reduction is very easy. Yes.
Getting the protons, for that we need water getting oxidized to oxygen.
Yes.
That is difficult.
Yes.
So why don't we use some other counter reaction for getting protons?
Like?
I don't know, maybe something which is easier.
Yes. So anything that's easier, you know, that's things like, here you have a proton. Here you have a proton and a hydride. But you end up with CO2. So you get into the problem of how to capture CO2 and reduce CO2. That's even more difficult. And we lose CO2 in this process. So it's not sustainable, or it's only partially sustainable. And that's probably the simplest proton source that you can have. You know, if you use sulfuric acid, you just generate loads of sulfate. But you have nothing to oxidize. You cannot oxidize sulfate. So in the end, the oxidation equivalent is the hard bit. You can use a metal hydride, you know, magnesium hydride. Okay, but so you have to, then you have hydrides rather than protons, so you have to reduce the manganese or the magnesium. And that's not nice neither. So to make lithium 0 or magnesium 0, no. So this one will probably be the most sustainable. And you don't have, yeah, so if you have a good proton source, it's nice. I think people have tried a lot, but generally you get more, you get either more complexity or less efficiency. So what people have tried as well is to use amines as proton sources. And then you reduce the amine to imine. Quinoline to the tetrahydroquinoline and back. That works, but one way with huge pressure, 5 bars, 10 bars, and higher temperatures, so you have significant penalty. And of course, you have a fairly low efficiency. So if you look at the hydrogen coefficient, the hydrogen storage coefficient of such a molecule, you know, you use 8, 9 carbons and the nitrogen to carry 2 equivalents of dihydrogen. Or another one is to use so you form now you have different proton sources, so you make out of a silane, you make siloxide or an alkoxysilane. And you can regenerate this then. But here, what is the classic regeneration? Lithium aluminum hydride. So that's totally irreversible. To make lithium aluminum hydride, to regenerate your thing, it's terrible. It's inefficient. Because if you have the hydrides already to make lithium aluminum hydride, why don't you use those hydrides? So it's nice for storage, but I don't know whether it's efficient by any means. And the waste again, you know, how much weight do you produce for 3 equivalents of dihydrogen? So I think the simpler, the smaller, the better. And this solution here is compelling because it's totally circular. It's really like carbohydrate synthesis, but less complex. And you store it in dihydrogen rather than, so it's principally it's feasible. So that's why we try to connect, and then you can connect it, you can capture either the electricity or simply you capture the dihydrogen. But I think this is the easiest storage, this is the easiest carrier. So once we solve this a bit, we're much closer to a real system. And in fairness, we have catalysts now that do this in 100,000s of turnovers. So there's a light at least somewhere in the tunnel, maybe not at the end of the tunnel, but in the tunnel. So I think this would be by far the most compelling way of storing energy in dihydrogen, release it as fuel. And it can then replace all the gasoline, because if you have a catalyst, you don't even have to store the dihydrogen. This is your dihydrogen storage. So, you know, if you can tank an airplane with water rather than with kerosene, okay, water is much heavier. So maybe the airplanes become a bit louder. So that's why we'd like to have this, but ideally not, well, with CO2 it would be most elegant because we would immediately deplete as well the CO2 concentration, but that's illusionary. If you see the natural process to do this, you realize there's no way this can be easily mimicked by anything synthetic. So I'd say stay with the simple thing, but then we can do this. So the real issue is really the oxidation of water to oxygen, and that requires the 4 electrons and the 4 protons to transfer. We have the 3 different electron transfer processes. Unfortunately, water oxidation is in this regime. 4 electrons, 4 protons, we have to work on this. So that's it. So if you have to transfer protons and electrons, it's good to keep a bit in mind how these transfer processes work. And I've shown you here 3 examples how electron transfer is dependent on proton transfer. So one thing is that we see pH dependence. pH dependence means presence or absence of protons. So you'd see that this complex here, this ruthenium-4 oxo species, can principally be reduced to a ruthenium-3 hydroxy species in the presence of this osmium compound. The equilibrium, so the reaction does not work if it's very basic, if your solution is very basic. So then you keep the equilibrium totally on the left side and you don't have any reduction. If you have a basic, an acidic pH, however, the reaction goes very smoothly. Why is this? Because at the same time, the osmium, the electron acceptor remains exactly the same. But the proton, so the electron donor stays the same, the electron acceptor modifies if there is a proton around. If the proton can coordinate to the oxygen here, the oxygen is much less strong a donor, so it stabilizes lower oxidation states. So as the proton coordinates, the electron can be accepted. It's not after, it's not before, it's while, same time. And they looked at this very carefully. So they looked at what is the reduction potential of this compound on its own. It's high, you have a significant penalty to reduce the ruthenium in this oxo conformation. And we intuitively understand this. Oxos are strong donors. So if you have a strong donor, we stabilize high oxidation states, so reductions are difficult. You can also look at it from the other angle. How is the protonation of this compound? The protonation of this oxo species is coming with even a higher penalty. The pK is very high of this system here because the ruthenium is in ruthenium-4 oxidation state. It grabs those electrons from oxygen. The oxygen has not much electron density that it can share with a proton. So the proton binding is very weak. This is a very strong acid. Now once we have this system, it goes very rapidly. Once we push the proton on this one here, then the reduction is very easy. So if we look at this from an energetic profile, this is like the multi-step transfer. So this is an energy scheme. So we know that principally the ruthenium-3 hydroxy is more stable than ruthenium-4 oxo. So the reaction should work. But if we first protonate, we have a huge barrier to overcome, and then only a little one to get so that's the proton transfer. This is wrong. Don't copy this. So we have a huge barrier to get that intermediate, and then no barrier to go down. So this is an intermediate. So that's the transition of the H transfer, and that's the electron transfer. If we do it the other way around, still the barrier is high to make the ruthenium 3 oxo, and then we have no barrier to go back. So here we have first the electron transfer, and then we have the proton transfer. So in both cases the problem is this high activation energy. Yeah, and that's the 8 and the 17 kilocalories that you see here. So that's prohibitive from this reaction to go spontaneous. But at low pH, at high acidity, it goes spontaneous, and the reason is that we can form them both together. So you see this in this reaction here, where we have now the oxidant changed from an osmium 2 to a ruthenium 2 that now carries 2 protons bound to the oxygen. So they're both stable, but once we combine them, we have a very low barrier, and we get in no time, we get the ruthenium 3 hydroxy. And the reason is clear. The reason is that now, as the proton can transfer from the ruthenium 2 to the ruthenium 4, the electron can transfer at the same time. So if we do this together, that's what we call the proton-coupled electron transfer process, PCET. The reaction goes at very low energy. So whatever we do for water oxidation, we have to transfer 4 protons, 4 electrons. We can start thinking of how do we remove the 4 protons from 2 waters. Now you see, you know the energy barrier from getting from water to hydroxide. That's manageable. But going from hydroxide to the O2 minus, this is a hell of a job. Very high energy to generate an O2 minus ion. The same to oxidize water to the oxonium, then to the 2 plus ion is close to impossible. So the way to go is to go from water to the hydroxy radical, basically, then to go to the O0 element that can easily combine. Okay, so whatever catalyst we're designing for this type of water oxidation, we have to keep in mind that we need a redox active portion in the catalyst, and we need a proton transfer support for the catalyst. So ideally we can oxidize and remove protons at the same time. Then we have the chance to get a sustainable catalytic species. So proton scavenging can be done by very different ligand designs. Carboxylates are very good. Dearomatization, rearomatization, we've seen, is a concept to be used for water oxidation. Many more. The solvent plays a critical role in water oxidation. This is no question. The only solvent that you can use for water oxidation is obviously water, because anything else is easier to oxidize. So you start, if you use methanol or dichloromethane, you oxidize your dichloromethane. Good. Here's the issue with the natural system. So that's how the photosystem 2 is doing this. And you'd see there's 2 shots of light coming in, one in photosystem 2, one in photosystem 1. There's the water oxidation, oxygen evolving complex, which is a very complex structure. Do I have a picture? No. It's a manganese 4 system, 4 manganese atoms that are linked together with oxygens and the extraneous calcium. And the proposal is that each of the manganese is getting oxidized by 1 state. So you absorb the 4 electrons, and then the protons so the electrons are then transferred in a so-called Z scheme up via peptidic bonds, then put into cytochrome B, then transferred over to photosystem 1, where eventually they do the oxidation of ADP to ADP. So the electrons are stored or are used basically to drive the synthase motor. And the protons are helping to make the gradient to keep the motor alive. But very complicated. The interesting part is this manganese center. It is very efficient, it's very fast, has turnover frequencies of about 300 per second, so it goes quick. But it's not stable. About every half an hour, the complex degrades, a new complex has to be generated and put in place. Now manganese is abundant, so apparently nature has found a way. Synthetically, we have been much slower. So what people have started to look at is at so-called Pourbaix diagrams, where you look at your metal center and its oxidation state depending on pH. And you find that the oxidation may change, may be constant over some range, may change in different pH ranges. The interesting part is where the pH changes, where the oxidation is pH dependent, because that indicates that you change the catalyst, the complex at the same time as you oxidize it. So that's the regime where you have proton-coupled electron transfer processes. So you see for the ruthenium on the basic conditions to go to ruthenium 3, but then the second one is on more alkaline conditions. Here's the natural one, the manganese, that's electronic flip. So very pioneering work has been done in T.J. Meyer's lab in the US. Like 35 years ago, he developed a ruthenium, a dinuclear ruthenium center. That's 2 bipyridines that are coordinated to ruthenium. 1 oxygen is bridged, so that's this blue dimer, it's called. This oxidizes water in moderate turnover frequency, but it oxidizes water. So that was quite a sensational breakthrough, that actually a molecule can oxidize water. He used the sacrificial oxidant here, so for the half cycle it's good to only look at the oxidation, otherwise you're making your system a bit too complex. And then it took about 20 years to start optimizing the system. Tony Lobet had a bit of an improvement in putting the rutheniums together, and he got 13 turnovers in about 15 minutes. Now that's 1 turnover every minute. That's nothing to fuel a planet, but it's an improvement. And then the system grew further, and we had some iridium complexes, and you see at some point, where is it? With these systems, we can get very high turnover numbers, tens of thousands. And we can improve it even further. I will talk tomorrow a bit more about this. Now we didn't do any exercises. We have another hour, do we? Yes, we make a break and then we do some exercises. I thought it was already 4 o'clock. I gained an hour in my life, that's nice. So, okay. So some of those compounds now get up to 100,000 turnovers. Other ruthenium systems get turnover frequencies of 1,000 or 10,000 per second. So we now have improved out of this very rudimentary data. The field has improved magically to impressive turnovers. So that's more of dehydrogenation, transfer hydrogenation in a bit of wider context. We then leave the dehydrogenation, we go to other CH activation. Tomorrow, maybe after the break, we just do some exercises to see a bit how much you were asleep, how much you were receptive, and how difficult it is to follow my language. So we'll see. We'll take a test of everything.